Okay, all right, let's get started. So hello everyone, good morning and good afternoon. Welcome to the ASA section on statistical learning and data science monthly webinar. My name is Boxiang Wang. I'm from the University of Iowa, and I will be your moderator. Before we get started, I want to promote two conferences. The first one is our SLDS 2026 conference. This is our very own flagship event and will be held in New York City from November 1st to November 3rd. The second one is really exciting. This is the conference on statistical foundations of AI. It is organized and co-chaired by Professor Chu. The conference will be from November 13th to 14th at the Center for Statistical Foundations of AI at the University of California, Santa Barbara. Both meetings will bring together leading researchers across statistics, machine learning, AI, and related disciplines. I warmly welcome and encourage you to attend. You don't want to miss any of them. Now it is my greatest pleasure to introduce today's speaker, Dr. Annie Chu. Annie Chu is Professor of Statistics and Applied Probability at the University of California, Santa Barbara. She is the founding director of the Center for Statistical Foundations of AI. Her research develops statistical foundations for AI with interests spanning statistical learning, heterogeneous data integration, reinforcement learning, causal inference, trustworthy AI, uncertainty quantification, precision health, and multi-modal data analysis. She is an ASA Fellow, IMS Fellow, AAAS Fellow, and an elected member of the International Statistical Institute. During the past 3 years, she received the IMS Medaling Award, the IMS Harry Carvel Medal, and the SCSA Distinguished Achievement Award in recognition of her contributions to statistics, machine learning, and artificial intelligence. She currently serves as co-editor of JASA, Theory, and Matters. So today's talk is on representation retrieval learning for heterogeneous data integration. Dr. Chu, over to you.
Thank you, Boxiang, for a very kind introduction, and thank you for the invitation for statistical learning and data science for ASA section. So as Boxiang mentioned, that at the USCSB, we organized a conference, the first conference from our center called Statistical Foundation of AI. So I also like to encourage junior faculty and students and also postdoc to, I see the chat. Okay, yeah, thank you. To apply the travel award. So we receive a National Science Foundation support for this conference. So people are eligible to apply this travel award. Please apply. And priority is given to people who are contributed a poster and also first come, first serve. So we look forward to see you at the November conference. So today I'm going to talk about representation retrieval learning for heterogeneous data integration. And if you're interested in this work, you can go to the archive, download the paper. The work has also been accepted by JADA, so going to appear sometime soon. So this is joint work with my former PhD student, Qi Shi. He was a postdoc at Carnegie Mellon University. Now he just joined University of Minnesota as a tenure track assistant professor in School of Statistics, which is also Boxiang's former alma mater at University of Minnesota. So I give you a little introduction why we're interested in data integration. So this is a kind of like you do some basic research about the trend in statistical learning, machine learning, data science, or artificial intelligence. You will see this field itself growing really well. Starting 2000, I think the field is a flourish. We have more faculty, more students in this field. So the red trend is showing that people work on data integration the growth even higher than average machine learning and statistics and data science overall. You see the growth is about 4 times, over 4 times. And general statistics, general topic increase about 3 times. But there's a reason why data integration is a vibrant and a growing field. We know that these days, even though people talk about large language model and we're doing many large data, high dimensional data, but still we are short of data. So realistically, if you involve any study, it's actually very difficult to get a very large sample size, because I'm also collecting mobile health data myself. Even tried to collect 30 subjects observation over time. It took several years and have to go through many obstacles, such as you have to get, as long as you collect the human subjects, you have to go through IRB approval, which could take a half year or to 1 year. And the human subjects, whenever you collect the information, it's always very, very challenging and involve a lot of missing data and data monitoring, all these things. So therefore, in reality, that we hope to get a good enough sample size. The reality is that we don't have a lot of sample size for many studies. So this kind of problem is pretty well known, even back to 1904. So we talk a little bit history about the data integration, and people are aware about meta-analysis, which is you can trace back in Carl Pearson's work, which is published in British Medical Journal. So in that time, I think we already have this term called meta-analysis. And now we know this word is quite popular. Even Facebook decided to change their name to be Meta. So in this very early work, Carl Pearson particularly mentioned about 2 things. So they tried to study about the incidence of the inocular fever. And they have 2 populations. One's the Indian population, one's South African population. And in his study, he also noticed that the South African study, the sample size is quite small. And therefore, he said, with such small sample size, it is actually very difficult to draw definitive conclusion. Okay, so in this article, we are already aware of 2 things, that you might have a 2 population. You do the same kind of study. This could be disease or could be some social problem or policy, but you have several different population. And this different population impose this heterogeneity. So usually like you collect different data from different sources. Due to many reasons, population itself or the way you collect the data, they are not homogeneous. So in this article, they also mentioned this, not just heterogeneous subgroups, you also have small sample sizes. So how can we do this, use this type of data to help us to draw more definitive conclusion, right? So this is a general problem. When you have this kind of research, you always ponder this type of problem also. So if you want to do data integration, so it's come very naturally. You have a different source of data. You want to learn something out of this data, and therefore you can utilize all this data. So the question, if we want to do data integration, what is the foundation to do data integration? First, they must have something in common among this different study or among different sources. Otherwise, how can you do data integration if they are completely heterogeneous, completely nothing in common? But for this type of a study, often we have challenges, which is we have different types of heterogeneity. And I'm going to give you more details a little bit soon. So this different type of heterogeneity also complicates this data integration method. Okay, so I give you some motivating example. You might be a little bit surprised what type of heterogeneous data we can do data integration. So this data set, some of you might be very familiar. If you teach deep learning or you're doing this recent work for the imaging analysis, this is called MINIS data. MINIS data is kind of you doing this categorical classification. So the first data set is an Arabic number from 1 to 0 to 9, a handwritten Arabic writing. The second image data is Japanese writing, also 0 to 9. And some of you, if you learn the Japanese, you might recognize some of the character. And the third image we call fashion minister data, which is also classification for different type of clothes, like pants, shoes, or blouses, or shirt. So we call fashion minister, but it's also black, white images. When you look at these three different images, of course, you immediately recognize the heterogeneity, that you can see the image looks very different, right? And this, if you want to put this as a distribution type of a sense, you can imagine these three type of images, that distribution are very different. And also classification task, which labeling could also different, especially, let's say, fashion minister data. You not just have a 10 category, you might have more than 10 categories. So therefore, the outcome could be different for different data sets. But on the other hand, if you want to see some similarity, it might be difficult for your human eyes or just by doing visualization. You notice that some important features, such as the edges, curves, and strokes, they might share some similarity. Even these three different image data sets look very different. Okay, so let's poke into more details, see how we actually see some common information shared by these three different data sets. So let's first try to do some dimension reduction. Let's say you use a ResNet to try to extract the singular value decomposition based on this 512 dimension. You first reduce the image size, then using low dimension image size to extract the singular value decomposition singular vector. And this is the picture what we see. If we using this heat map to use a minister singular vector versus the k-minister singular vector to draw the heat map. So this is 3 heat map showing this pairwise singular vector extracted from these 3 images. And as you observe that minister data versus Japanese minister data, this off-diagonal part, you can see kind of more enhanced red color, showing they have some correlation going on. Although minister data versus fashion minister data or k-minister versus fashion minister data, you don't see very clear pattern, but you still see some off-diagonal part, the counter-diagonal part, not off-diagonal part, that have some enhanced red color. First, we observe some heterogeneity, that there's no singular vector are exactly shared among all these 3 data sets. But we do observe some singular vector are more similar among 2 data sets. Okay, so, and also we observe the minister and the k-minister are more similar than their similarity with the fashion minister data. So that's not surprising, even though it's Arabic writing or Japanese writing, it's all about 0 to 9 handwriting character. So therefore, they show more similarity compared to the fashion minister data. So this is the first example. We already see that these 3 data sets looks different by visualization, but still they might have some information to share. And we're going to come this later. How can we learn this shared feature? The second motivating example, I think it's often more relevant to the health study and a medical study. This we also call the multimodality data. So this data set is from Alzheimer's Disease Neuroimaging Initiative, ADNI data. I know some of you analyze this data. There are many different kind of ADNI data. So this is the one ADNI data. We have the 3 modality and one MMSE as the outcome variable. So these three modalities have two other image modality, the MRI imaging and the PET imaging, and the third one is genetic information. So notice that each modality could contain many variables. Some could be over 1,000, although here genetic information we have about 300, but in other data set you could have a much high dimensional information for genetic data, genetic modality. The MMSE is a mini mental state examination. This is a subjective measure of mental health status to measure the Alzheimer's disease progression. So, so as we notice that for this data set, we have a different modality. And another interesting part is that some modality, you have a completely block missing information. So here we categorize our data to be four sources of data. Source one, we have a complete modality. All this modality, we have about 69 subjects. And the source two, we have 96 subjects. However, the genetic information containing 300 variables, they are completely missing. So this is also pretty well recognized in many data collection that the missing data is not due to, let's say, completely missing complete at random or missing at random. This could be informative missing. So doctor might view the patient doesn't need to have certain modality information. Boxiang, do I have something here? I see. Should I stop? There's some question here.
There is one question.
Yeah, go ahead.
So the K-minus data are Japanese characters used to write syllables. The commonality with MNIST is the construction from the written lines. Yeah, I think this is like a comment.
Oh, okay. All right. Yeah, the comment is correct. Yeah. So yeah, the Japanese character is also 0 to 9 in Japanese handwriting. So all these are handwriting images. Okay, thank you. So we continue on this. So as I mentioned, that different modality, so for some modality, one particular source, their modality could be completely missing and could due to the informative missing. And we don't know the reason. The doctor might, so for example, a lot of us went to a hospital probably multiple times. So far, I've never get my genetic information collected. So there must be reason, okay? So doctor either think there's no necessary to collect my genetic information. They also have other reason, let's say health insurance is not going to cover these measurements. If doctor cannot justify there's a necessity to collect this type of modality, the doctor is not going to collect everyone's modality information just because, let's say, statistician wants a more complete modality information. So in reality, this observational study, we have to accept that a certain modality for a certain group of patients, they are completely missing. Another thing I want to mention, so these days, people also try to use synthetic data or data imputation. So for this type of a data, when you have a completely missing block information, you try to generate synthetic data or using, let's say, multiple imputation, this type of imputation method might be problematic, okay? So how could you, in some sense, the doctor is not going to be convinced that you impute a data which may be based on observed information, but there's no base on this imputed information. And if your conclusion is depends on this synthetic or imputed information, the doctor or patients may be doubtful about the conclusion. So this is something keep in mind that there could be a potential problem just try to impute the missing data. Okay. So the reason I'm using this motivating example is try to show you different type of heterogeneity. I want to show this. So here we make this, so we kind of ignore the M4 equal to 13 because the sample size is quite small. Let's first focus on the first three sources of data. The N1 equal to 69, N2 equal to 96, and N3 equal to 34. We want to see this different type of a source, even though we call different type of a source. It really because due to the different missing mechanism, okay? Due to their different missing pattern, we put them as a three sources. So in some sense, artificial three source, but it was used as evaluate a different missing situation. So let's look at this distribution heterogeneity. Even though it is a lot of high dimensional data, let's just try to simplify, okay, do some visualization. So if we try to get a principal component from each source of data, at least we just, it's not really kind of very thorough examination about distribution heterogeneity, but still visualize can tell us what's going on. So if we use the first principal component versus second principal component for these three different type of sources, we observe they already show this distribution heterogeneity. So for example, the center is different, the spread is different, the outlier is very different. This is not surprising. So even though it's all from the ADNI data, and we kind of make this resource of data based on the missing pattern, we already saw that the distribution is quite different. Just using the first PCA, first principal component versus second principal component. You can do something further. Let's say you have the several variables. You can check their distribution plot. But this is just a quick way to evaluate. So here, when we talk about distributional heterogeneity, we actually try to emphasize there's a discrepancy of the marginal distribution across the different data source. And we also term this as a covariate shift. Okay, so there are different terms, but the covariate shift, they mentioned this, the marginal distribution are different from across the different data source. The second heterogeneity is also pretty common, that the marginal correlation between the first, let's say between the covariates among the MRI and the outcome, let's say MMSE, we use it as outcome, is also different across the different data source. What does that mean? That means if you just look at the association between the covariate and the outcome, and this association between covariates and outcome are quite different across different data source. Okay, so you can see the left figure. So we here have three different sources. So some correlations show positive. On the other hand, the same correlation corresponding to same covariate versus MMSE, they are negative or just around 0. Okay, so you can see some actually the spread is we just kind of randomly pick 50 covariates from the MRI information versus MMSE. So this posterior, we call this a posterior heterogeneity, even though this had nothing to do with the Bayesian analysis, showing this, the discrepancy of this conditional distribution of the response given the covariate information across the different data sources. They are quite heterogeneous. And we also term this as a posterior drift. Okay, so you can see the association is different. The third type of heterogeneity we call observational heterogeneity. So we already mentioned that each data source observe a different modality and leading this block missing pattern. Okay, and this missing mechanism can be complicated and intricate, which we might not know the true reason why they are missing. Okay, so therefore, if you just try to rely on the imputation or other synthetic data generation, often depends on the assumption, which is like, let's say you believe there's some assumption there, and this assumption we have no way to verify. So this type of heterogeneity we call observational heterogeneity. And due to the observation nature and that we have a chunk of the data are missing. Okay. So the question comes to, can we integrate the multi-source, multi-modality data to train this prediction algorithm? So therefore, we can accommodate this distributional or posterior or observational heterogeneity jointly. So build a unified framework, not just, let's say, do this particular heterogeneity alone to develop our algorithm or method. Okay, so this is a question. So this is some literature review, although there are a lot more. If you read the recent, because we have revised our paper several times, so the literature will be more comprehensive if you go to the manuscript. But in general, I think the work on this data integration can be classified about 3 types of approaches. First, called distribution heterogeneity. So if they focus on distribution heterogeneity, the very well-known work called Joint and Individual Structure by Eric Locke's group. Okay, so the idea is to decompose the matrix decomposition. So they either have the row factor or the column factor share among other data sources. So this is kind of a general idea. So in general, they also believe partially shared structure using this matrix decomposition. The second type approach is really try to focus on posterior heterogeneity. So for example, like a transfer learning, multitask learning, or domain adaptation, all this type of work try to address posterior heterogeneity. But in general, they also require the same model for different data source. So this could also be restrictive. So when you have a different data source, the same model assumption might not valid. We're going to come back this later, okay? And the third one is to target this observational heterogeneity. So for example, imputation method, because you have a missing data, naturally people think about how to impute the missing data. Then they also have non-imputation method, which we will also compare numerically in the end of the talk. But I want to emphasize most existing data integration methods incorporate one or at most 2 types of heterogeneity. And really, they're able to accommodate the 3 different types of data heterogeneity. So here, I want to mention that today my talk is going to build a unified framework, what we call representation retrieval, R², and which can accommodate this multiple type of heterogeneity. One, we already talked about distribution or covariate shift, or posterior heterogeneity, we call a posterior drift. And third one is observational heterogeneity when we have a block missing situation. So here we're going to introduce a novel penalty we call Selective Integration Penalty, SIP. And using the SIP, we're able to improve the generalization error of the R² framework. Okay, so in theory, we will show that we can control the convergence rate of generalization error and showing what this convergence rate are affected by what kind of factors. And also numerical, we're going to show that using this our data integration, we can improve real data situation really well. So first, let's look at a problem setup. Let's try to keep the notation as simple as possible. So here we have a different source of data. So so S is from 1 to S, big S. So XS means the covariate information from source S. And the response YS is also just like it's observed response information from the source S. And here we allow this distribution heterogeneity in a sense that across different data sources, distribution of the same covariates can be distinct. That means you could have a different distribution even for the same covariate information. The second one is across the different data source. The conditional distribution y given x can be different. Okay, in a sense that our model could be different. You don't need to assume the same model for different source of data. The third one is that across different data sources, the covariate X may contain modalities that are unique for this particular source, or modalities shared by some other data source. That means I could have a variable information for this particular data source that other data source, they don't have it. So in a sense that we don't need to impose that dimension has to be the same for the covariate part. That means a different source, very naturally, you're collecting some information I didn't collect. But of course, it doesn't mean every data information you collect differently, and then you have no foundation to do data integration. But at least the partial of the covariate information that they are unique by itself. And they could also have a common demographic information they all collected. Let's say the gender, age, BMI, and some common information they're able to collect. And the goal is try to learn predictor, this FS, is how can we from XS learn the response YS. So therefore, this predictor information is source specific. That for particular source, this F is different. So they don't need to have the same F. Okay, so here's what our proposal. Let's first going to focus on the first two types of heterogeneity. Although the framework is the same, the distribution heterogeneity and posterior heterogeneity are going to separate from observation heterogeneity, even though the framework is the same. Okay, so first let's look at a method overview. How can we using representation retrieval to do the data integration? So first, let's look at the true data representation. So let's say we have a different source of data. I kind of simplify. We have 4 sources of data. And each color means data representation. You can also think about, let's say, in linear representation, that's your principal components. Okay. So the different color means a different representation for this particular data feature. So first, let's say we get representation dictionary, collect all this different representation from all this data source. We have the different color. And then through the representation dictionary, we can retrieve the representation which is relevant for this particular data source, let's say V1 to V4. But as you see that the blue color on this true data representation, V1 to V4, once you do this data integration, when you retrieve the same color, let's say blue color in the V1, source 1, is able to, in the retrieval process, we are able to learn the blue color information, not just from the source 1 alone. We also learn the blue color from the source 2, because both 2 data sources contain the blue color information. So similarly, for other color, let's say the light green color, you have this this light green color data representation in all 4 sources of data. So therefore, when you learn this light green color V1, you're able to combine all the light green color for this 4 data source and learn this light green color, V1, V2, V3, V4. So you get some general idea. When we do representation retrieval, we sort of decompose our data to be smaller pieces. And some pieces of data representation, they share. And some pieces, they do not share. That's very natural. Let's say the dark green color, it's very unique. It's by source 3 alone. Then you will only use it for source 3 alone. You're not going to borrow the dark green color to source 1, source 2, or source 4. Okay, so this is kind of a method overview. So here, as I mentioned, then when we do representer dictionary, we store all this information, and we notice some representers are fully shared, like a light green color, and some information are partially shared, like the blue color or the pink color. But some other dark green color are unique, not shared with any other data source. We all get this information, okay? So this is a motivated paradigm, what we call partially shared structure. So we all heard about this elephant, blind person touch the elephant. So in that story, what we learned that if you just touch a part of the elephant, you only know one feature of the elephant. Therefore, you don't see the entire picture of the elephant. I'm going to use this as the opposite way to view this data integration or partial shared structure. Let's say if we want to impose a fully shared structure, that means everything had to be the same. That means when you try to learn this elephant, you want to use any subjects which exactly it's elephant, right? So in this situation, the commonly shared components is assumed for all data sets. And therefore, that limited data sets can be integrated. So if the data sets is not elephant, you say, because I want to impose this fully shared structure, so therefore, I have to exclude this type of data. So therefore, this integrative structure is fixed and imposed. However, if we say we only need a partially shared structure, we don't need a fully shared structure. Therefore, we can relax this much loosely in a sense that the multiple components can share by a subset of data. Therefore, more data sets can be integrated. So if you have a data set like a fan, and they have some similarity of the elephant's ear, and this fan's data sets can also be borrowed when you try to learn the elephant. So therefore, integrative structure is adaptive learn from the data. So this is the contrast that we can say we can use a partially shared structure. Therefore, more data sets can be integrated. Anything similar, any partially similar to the elephant, this data sets, we can also use it in our data integration. So here's our more details, how we do the data integration. How do we do representation retrieval? So this is a representation retrieval matrix. So this is a dictionary. And if we for the source one, if we want to learn source one, we notice that this feature we can use the blue, pink, red, and the light green. So therefore, this is the matrix, representation retrieval matrix, which is 0, 1. So all this data feature, we're going to use it, we put a 1. And the data feature, for example, this two other kind of a green color, not useful for the source one, we just put a 0. We're not going to do negative transfer, that we're not going to use any irrelevant information from the dictionary. Okay, so therefore you build this retrieval information, only use the data representation which are relevant for this particular data source. And in the meantime, we also notice when we do this retrieval-based integration, each column select a representer from dictionary, but they do not play equal weight. So we notice, for example, the second representer is retrieved 3 times for these 3 different sources. That means the second representer, the weight, the usefulness is useful for source 1, source 2, and source 4, but not for source 3. And another representer, let's say the light green color, is used for all these 4 sources. You can see this all there. So they have a different weight. And the last representer is only retrieved once, the dark green color is only used for the source 3, not for any other source. Okay, so we actually also see the differences when you do this data integration, try to retrieve this representer information. So therefore, we impose what we call the selective integration penalty function. So the idea is try to enhance the integrative representation learning. So we try to encourage the integrativeness of the representer. Let's say this representer is used more frequently or for more sources. We're going to encourage it more compared to some isolated representer only used by one unique source. So this SIP penalty is used this way. And I can explain this easily. So you see that, let me look at the next slide. Let's say if all representatives are retrieved by all data source. Okay, so this representative is very useful. All the data sources need this representative. When you do this double summation, this S means the total number of a source. This double summation, this indicate function will end up to be S because all representatives are retrieved by all data. When this representative are retrieved by all data, so it's S, and therefore the minimum value is 0. Okay, so that means we're not going to impose any penalty for this representative because this representative are retrieved by all data source. And in contrast, then some representative is retrieved at most once, like the dark green color. So when you do this double summation, that only end up to be 1 because only one data source use it. And therefore, this minimum is a 1 versus 1 is a 1. And when you sum this up, that's a D. Okay, so therefore, if the representer is only retrieved by one source, and this representer, we're going to penalize more in the sense that it is only going to be used for this particular data source, but not going to be used for other data source to prevent a negative transfer. Okay, so minimizing this SIP penalty encourage representers to be more integrative. So this is the purpose for the SIP penalty. And this computational complexity for using the SIP penalty is linear versus if you use a fused penalty, like you try to fuse things together, that is a quadratic complexity. So therefore, this computation complexity is a lot less if you're using other type of a penalty. Okay, but practically, when you use a SIP penalty, we also have the optimization issue. So here, the retriever are binary matrices, and therefore, the SIP involves this non-smooth indicator function leading to this NP hard optimization. Remember that when we do variable selection, if you're doing the L0 penalty, that's just like doing the subset selection and end up to be the exponentially NP hard optimization problem. So therefore, we're going to use two types of a remedy. The first remedy, we try to pack this retriever and the learners as a sparse-induced learner. And the second remedy, we try to propose this smooth surrogate of the SIP penalty. Okay. So another actually things I didn't mention earlier, when I talk about this retriever matrix, you might wonder, how do I know which representative I should retrieve? I don't have a prior information. So how do I determine this binary retriever matrix? So here in remedy 1, we're actually going to address this problem. So here, this is our learner, Fs, and theta is our representer. This is theta we actually need to estimate through the optimization process. Remember, we have a representation information. All this different pieces of theta is what we're going to estimate. And this is the retriever matrix. And this alpha is a coefficient. What is how many of this are we going to retrieve for this particular source as this is like a coefficient. So mathematically, it is equivalent to this learner is equivalent to pack this representation retriever matrix and alpha as a coefficient together. So we call this beta S. Okay, so therefore we actually using this remedy 1 solve 2 problems. that we don't need to specify particular RS. We also, using this sparse learner, learn this which representer is useful. So if this representer is not relevant, then this beta S is close to 0, and then we will not retrieve that information for this particular data source. Okay, so this part is just like a L1 type of penalty. The second remedy is how to make this surrogate function, how to make this penalty function as smooth as possible. Remember, before that was a double summation with the indicator function. And here we see that if it's a 0-1 penalty, so it's a non-smooth. So here we try to call using this truncated L1 penalty, in a sense that we connect this 0 and this penalty, make it a continuous function. What does that mean? That here we actually introduce additional tau function. So when this tau measures this gap between this gap, if a tau is very small, this gap is very close. So when tau is small, this surrogate smooth function is very similar to this 0-1 penalty, right? You can see when the gap close. On the other hand, if a tau is big, then this is much smoother compared to tau is small. And so then make this optimization relatively easier. So, so you connect this to the SIP penalty, it's like this. If this information, let's say this representer is only used by one particular data source, we're going to penalize most with a 1, okay, when you do the double summation. And when you have S source of the data, they all use this representer, then we're not going to penalize at all. So it's like moving the penalty 1 to 0, okay? So this is so remedy 2, that we try to make a surrogate function, so make this as smooth as possible, okay? So now come to the loss function, the objective function. How can we do this data integration method? So this loss function can be very general. So could be cross entropy loss for classification, and could also be L2 loss for regression. So you can use your type of loss function, could be negative log likelihood, or could be any type of entropy type of a loss function. Okay, so in general, in the loss function, to measure the discrepancy between the response and the predictor, using this your representer theta and your coefficient beta. So we need to estimate theta and beta, this based on the observed information. So theta is a function of your xs, which is your covariate information, and beta is your coefficient. Then you have 2 penalties here. So first, based on remedy 1, you have the L1 type penalty. So if a beta is very small, you're going to shrink towards 0. Okay, you have the tuning parameter lambda 1. And the second type is SIP penalty, which try to encourage, am I okay? I received, say, Zoom.
I think it should be fine. So
okay, all right, yeah. Yeah. So yeah, as I mentioned, I cannot read the chat box really well, but I'm going to address people's question when we finish this talk. Okay. So the second type penalty is SIP penalty. It tries to encourage the integrativeness. So this part is, as what I mentioned, that if the representer is useful for all data source, we're going to penalize less. And here we also have a lambda 2, another tuning parameter. So in the implementation process, this tuning parameter need to be tuned through validation part. So you have a training, validation, and a testing set. Okay, so this is overall the objective function. So let's go into recap what we're doing for this R² learning. So first, we have the representation dictionary. You can view this as a different color. different shape of the Lego block, and this is our representation. And when we do the retrieval, it's always the task-oriented learner. So if you want to build this particular task, let's say you want to build a car, you're only going to retrieve the relevant shape, relevant color of the Lego block to build a car, okay? But when you retrieve this red color, notice that this same color, because also was used for build the Magic Kingdom for the other task, this same Lego block can be reused, not just for particular task, can also be used for the other tasks, which they also use information for this particular color, particular shape. But then the third task, which is the Eiffel Tower, which is a very unique color, and therefore they can retrieve this particular color shape by itself. So therefore, this R-squared learning tells us that we try to avoid the negative transfer. On the other hand, we also borrow as much information as possible from other data sources. We share the partial information on this data feature. Okay, let's look at how we also use the same kind of framework for this multimodality block-wise missing type of data. So this is the multimodality block missing data. So this, again, I try to simplify. We have a different modality, let's say 3 modality. And we have a data 1, data 2, data 3, the different source based on different modality. So the light color means this entire modality is missing. And you can see that first, there's no data source. So we have a complete observed modality information. And source 3 only have a 1 modality information observed. So so first we notice that if we try to integrate all modality information across all data, might be infeasible, okay? Because let's say the modality 2, we only have a 2 data source. So we don't have a 3rd data source. And it is also risky to impute missing modality due to complex missing mechanism. We notice that it's just not missing at random or missing completely random or missing sporadically, or some data is observed. Here's a completely missing. How could you impute the missing data? Okay, so, but we also notice that some data source might observe the common modality. For example, data 1 and data 3 observed modality 1, the blue color. And data 1 and 2 observe modality 2. So it is also possible to integrate overlap modality information across different data sources. Okay, so here's our approaches. First, how can we learn this representation? So first, we can think about theta 1, theta 2, theta 3. Let's make it more concrete. What is theta in this? The previously, it's more like vaguely, you can see the representer. Here's a little bit more concrete. Let's say theta 1 is representation for the modality 1. And theta 2, theta 3 are representation for modality 2 and 3. And theta 4 is a representation for modality 1 and 2. So therefore, this example also tells us we don't require all this representers. They don't need to be orthogonal. So you know the theta 4 is overlap. It's like a 2 modality interaction term, theta 4. So therefore, theta 4 is not orthogonal to theta 1, and theta 4 is not orthogonal to theta 2, okay? And theta 4 can also be interpreted as something co-occurrence for 2 modality. So we don't know why theta 1, the modality 1 made up modality 2 in certain data, they coexist. We just put as a representer. We represent that you could interpret as interaction term or the correlation information or coexistent information. And similar, theta 5, theta 6 is like a 2-way interaction for pairwise modality. And theta 7 is a coexistency for the 3 modality. You can view this as a 3-way interaction effect. But reality, not all the representers are identifiable, Okay, we can see theta 1, we are able to observe from both theta 1 and theta 3. And theta 2, we are able to observe from theta 1 and 2. Theta 4, we are able to observe from theta 1. However, theta 5, which is the two interaction for modality 1 and 3, we don't observe any data set containing modality 1 and 3. Therefore, this gray color means we are not able to have this information. And similar to theta 7, there's no coexistence for 3 modalities, so therefore it's also gray color. Okay, so this we recognize some dictionary are not identifiable due to the observational study based on observed data. Okay, but nevertheless, we can still do the data integration as follows. So we can learn theta 1 through theta 1 and theta 3, and learn theta 2 through theta 1 and theta 2. Now, because theta 1, theta 2 are learned from both data source, therefore we can use SIP penalty to learn theta 1 and theta 2 better. Okay, and when we try to learn theta 1 representation, we can use theta 1, we can use theta 2, but when we use theta 1, the theta 1, we also borrow information from theta 3. And when we learn theta 2, we also learn the theta 2 through the theta 2 information. Okay, and in addition, theta 1, theta 2, for theta 1, we also learn theta 4, which is a two-way interaction of a modality 1 and 2. So therefore, we have a 3 type of information, theta 1, theta 2, and theta 4, and theta 1, theta 2 is like doing the SIP to learn this information from multiple data sources. Okay, so similar to data 1, data 3, you can see this is how we learn the data integration without doing multiple imputation or synthetic data, but still able to borrow relevant information from different sources of data. As I mentioned earlier, this is the same unified framework. So therefore, the objective function is still a very similar form. We have first part is a loss function, except this we also have summation because we have a multi-modality, M1, M to 1 to big M. We still have a 2 penalty function, the L1 penalty and the SIP penalty, which try to encourage integrativeness of the representation. Okay, so this is like showing how can we do blockwise representation retrieval learning. The only something different for this, the third type of blockwise data integration is how we learn this data representer through this different modality. Okay, so if you have a multi-modality information, you might have a different way to learn the modality, but this is a one approach to learn borrow information from multimodality. Okay, so I'm going to talk a little bit briefly about the theoretical question. Very naturally, what is the benefit? If we're doing data integration, are we going to reduce, let's say, generalization error, right? So here we categorize generalization error using this called excessive risk bound. Excessive risk bound, that means if we have oracle information, theta, all the star means oracle information, you also have a risk. The risk is based on the average of the loss function, once ys, once your predictors. Okay, the excessive risk, that means based on our method compared to the oracle information, what is the excessive risk? And we hope this excessive risk converge to 0. Okay, so here's our information that there are 2 things we need to, so even though notation looks a lot, but you need to remember first, this rate of convergence depends on number of sources of data. So first, remember each representer learn different source of data. So it's not like they are all uniformly learn the largest number of sources of data. Some representer only learn small, some learn the bigger. So therefore, this gamma characterize average number of data source retrieving each representer. So this has a low bound by eta. Okay, so we imagine if eta is big, that you borrow more information, then the convergence goes faster. The other one, remember, we have several approximation error. First, we're using representer to approximate our data feature, the theta, right? So they have approximation error. We also have this surrogate, a smooth function to approximate our SIP penalty. So this also have approximation error. So therefore, the G has upper bound approximation error by pi. So eta and pi. So keep in mind, this is useful. So excessive response is bounded by 4 terms. First term characterizes the complexity of learning the representation, like how complex we learn the representation. The second is the cost, approximate SIP with a relaxed SIP. And the third is the cost of learning data source specific learner. So this is a very more usual third term. And fourth term characterizes the complexity of learning from this NS random sample. So typically third and fourth term is very common. And the first and the second is unique for our data integration. Okay, so give you a little bit more details. So first, the SIP controls the first 2 terms. When we have a large penalty coefficient lambda 2, this leads to a large eta. That means we encourage more data source, average data source for the representer to borrow information. And also smaller approximation error. Okay, so therefore, improve the convergence rate. So when your eta is big, when your pi is small, this leads to the convergence rate close to 0, goes to 0, and therefore benefit us. But on the other hand, the fully shared dictionary could incur overfitting issue. So therefore, this lambda 2 have to tune properly. So that doesn't mean large is better. You have to make sure you also don't have overfitting issue. And in addition, the tau also play a role. Remember, the tau is measured how this SIP penalty, the surrogate smooth truncated L1 penalty, how this close to the L0 penalty that's indicate. So the first term as monotonely decreasing, that means when tau is smaller and the first term is also smaller. Remember, the first term tells us a complexity of the approximation error. So if a tau is small, it's close to the true function, so therefore it is smaller. But the second term is monotonely increasing. Second term is a cost. And when tau is small, you also cost small. And so therefore, this tau is also, you need to balance it. It cannot be too small or too large. You balance the first and the second term. Okay. So due to time limitation, I'm going to skip the simulation. I'm just going to the real data analysis. I hope this real data, 2 data sets will be useful for your study as well. The first one we mentioned about, we haven't mentioned yet, this is called pan-cancer analysis. So you have 5 different study different cancer, like melanoma skin cancer and the colon cancer, lung cancer, pancreatic, and the breast cancer. So this is based on this, you have many measurements, you have a lot of genetic information, and the response is a tumor size shrinkage. And the covariate distribution are heterogeneous here among 5 tumor type. Okay, so this is not surprising because the tumor size could be very different and the feature they are collected could be different. But the conditional distribution of response given covariate are also unique. Okay, and certain genes they might share, but certain genes they might be very unique. For example, the BRCA1, BRCA2, these 2 genes are very unique for breast cancer. But let's say TP53, this gene is play important role for all type of cancer. So for this 5 different cancer study, it's not surprising that we have information to share, but we also have a unique genetic information or other feature that are only relevant for this particular cancer study. Okay, so this is our result using our R square. we usually look at the mean square error for the our method compared to other existing data integration method. So this is multitask learning. Individual, that means we only use this particular data source, not any other data source. And pooling means naively put all this information together without doing more intricate data integration method. Okay, you can see in all these 5 different cancers, our mean square error is smaller than other. And in particular, let's say a melanoma cancer, ours only like a 0.876. And the other method all above 1.2, and also similar to pancreatic cancer. Okay. And the second data analysis, we mentioned the adenine data. This time we're going to use all 4 sources of data, even M4 equal to 13. We treat it as another source of data. And this result, we're using the blockwise square learning, and this individual learning, and this discount. This discount is a non-imputation method. And because the multimodality information was unbalanced and missing completely, with a block missing data, it's hard to find other method without, doing much change for other people's method to implement this one. So therefore, we can only apply individual learning and the discount method. You can see for all this data source, our MSE is lower, okay? And another lesson we learned that if you don't do right data integration, and especially if this 4 sources of data are very heterogeneous, the individual learning sometimes not the worst and could be beat other type of a data integration method, okay? So here's a summary of today's talk. We talk about unified framework for this heterogeneous data integration using R² and accommodating 3 types of data heterogeneity, distribution, posterior, and observational heterogeneity. And we didn't talk about interpretation of a shear structure, but I think this is a very interesting direction to go, that if we're able to do some data visualization to interpret, to do interpretation of the shear structure or unique structure. What does that mean? What is, let's say, genetic information, immune system, how this contribute to the final prediction? And we talk about selective integration penalty, SIP penalty. We really try to encourage integrativeness of the representation learning. So we notice some representers are more relevant for particular source, some representer is less relevant. And we also talk about blockwise representation. So this is also could be potential future direction. Let's say so far we didn't talk about the dynamic longitudinal data. So how can we extend the representation retrieval to time variance signal? Especially have a longitudinal data, you have unequal repeated measurements from a different source of data. This is although we already talk about, we don't need different source of data, have the same dimensional data, but even within the same data, the longitudinal measurements for multiple variables, they could be time variant. So especially, let's say you do mobile health data, you measure physical activity, heart rate, and deep sleep, sleep quality. These measurements, even from the same subject, the resolution are very different. So plus the missing data due to the observational study, how can we integrate this information within subjects and across subjects? Another important thing I haven't talked about modality disagreement. So far, we talk about different modalities. They might have a complementary information to enhance the data integration. But in some certain situation, modality could be misaligned and have a disagreement. So for example, if you're reading the YAP review data, your text review and your numerical review, they might contradict each other. So how can you deal with this kind of modality disagreement? And also sometimes you watch the video that whatever the person said in text and the person's expression and the audio, the video and the audio might contradict to each other. So how can you learn this disagreement and utilize this modality disagreement to truly recover what is the true meaning of this person is talking about, right? So some people just say talk, the text information may be very different as their expression. So how could you learn this conflicted information? And also different response structure. So let's say you have a different scale, although we talk about different scale, different dimension, but how can you accommodate? We have multiple responses. So far we talk about univariate response. You have multiple responses with a different scale and dimension. How could you handle this kind of data across different data source? So thank you. And also I advertise our center a little bit. This is the center logo for Statistical Foundation of AI, which we just launched this May in UCSB. So thank you for your attention.
Yeah, thank you very much, Dr. Chu, for this excellent talk. Now let's stop recording and we will open the floor for questions. Stop recording.